Hello, I think we are in live. Okay, good morning, good afternoon, everyone. Welcome to the CSE365. We continue with our binary exploitation lecture. Last class we saw shell coding, and we continue with the current module of memory errors for this lectures, and then for Thursday we will look over the program exploitation, and then as mentioned in the announcement by Connor, we will have up to April 29th, Monday, due date for this assignment, after which you can complete any other challenges with 50 percentage of score, and up to May the next week, the date which mentioned in the announcement. Let me open the pwn.college. Sorry about the delay in starting this session. There was some minor glitches in the camera. Okay, so we were in the final week of the module. So we went over some of the shellcode injection, and this week we will go over the memory errors, and the program exploitation we will just cover in the Thursday. I hope the corner also covered yesterday some of the modules, some of the challenges in the office hour. Um, so we said that we saw that the shellcode binary exploitation is nothing but the exploitation of the vulnerability from the binary level. So it provides a better chance of having a complete control over the resources compared to other kind of injections that we saw in the previous module for web security, meaning the script cross-site uh, script injection, or SQL injection, or code injection. In this module, we will be looking at the injection of code at the binary level, and we also saw that um, uh, the shellcode, we, because of the one, most of the architectures are one human or architectures, and in which the program and data are stored in the same memory. uh, because of that, it's possible that code get injected into the memory and being executed as a part of the data, and it's provide the opportunity as we as the attacker, ethical attackers, to inject the code part for any vulnerability, and then direct the control of the control of the program flow into a specific part. So in the previous class, we saw that how to inject code such that it will spawn a shell, and from the shell we would be able to make a complete shell process. We would be able to make a complete control of the resources um, using the shell code. We continue with the same thing. So the method of injecting any shell code or other thing would be through memory, in which we find some vulnerability, usually in the buffer provided in the stack, and we use them to inject code or direct the control to specific uh, code part that will help us to make complete control over the code. So the main thing is that we find vulnerability from the memory, and because of the one human architecture in which the code and memory are most of the architecture are x86 based, and since uh, um, the memory and the code are all saved on the same memory. We use that vulnerability to inject the code and exploit the vulnerability to specific target and use the resources. So what are the memory errors? So as we can see here, initially, what are the causes for the um, memory errors, and what we actually mean by memory errors? So if we can go with the history, originally the program was done using machine code and assembly programming, and as the name indicates, assembly is the assembly of the machine code. So that was nothing different from the assembly code. So it's giving a mnemonic to be a human recognizable mnemonic, but it's the same as the machine code that we saw in the assembly crash course. And that doesn't that's not easy for the human level of understanding. And there were attempts as early as 1952 to make human high level programming language and then compile into code. So as you can see here, Grace Copper was the first to propose for early attempts of using compilers for high level programming languages. But in those time, the compilers were not efficient, they were slow, and it's not practical enough to be used on in a practical scale uh, for a common task for programming. And then in 1972, Dennis Ritchie created C, and with C, he recreated the Unix operating system. The advantage of C is that it's reasonably portable. You can adapt to all the different languages, and at the same time, it's a high-level programming languages. But at the same time, it provides the full flexibility of complete control over the all the resources of the machine, exactly similar to the assembly language. Because of that popularity, it became quickly become popular and used by everyone for programming. Uh, but the flexibility, the power it provides to have the complete control, similar to the assembly language for the complete resources, also provides uh, uh, with great power comes, as people used to say, great power comes great responsibility. It provides us a lot of opportunity to make uh, potential vulnerabilities or mistakes, uh, and get us into trouble. So before going into the details, this is some of the timelines about the progress of the languages from the assembly to modern high-level programming language, in which the language would be compiled into a machine code. So the C is developed and become popular around 1970s. But it's close to assembly. It's a high level programming language, but it's close to assembly, with providing a lot of opportunity to make a complete control over the hardware resources. But there is a security implication because um, of that close enough to assembly, without any precautions that inherently being implemented in the C. So because of the security implications, then the next languages try to incorporate some of the security features into the language itself. In 80s, C++ developed. Mainly purpose was to develop it for object-oriented programming languages. So it's not some C++ is not much different from the C in terms of security implications. And then VM based languages like Java came, in which developing into code and then deploying it to everywhere using the VM based machine code bytecode. And in those they started implementing um, uh, some of the security features, but still the compiled languages uh, are more dangerous enough up to 1990. So we are talking in the decades of 90s. And then gradually we progressed into just-in-time compiling in the 2000s. And then currently around we have the most of the languages started implementing the memory safe features. And currently the Rust is the most uh, talk of the town, as we can say. Even the Linux also has the plan to implement some of the Rust based thing into the operating system. So, so as we see here, the C has many vulnerabilities because of not having any safety features into the language itself. But C is still the popular language. So this slides developed by Professor Yan at 2020, I think. The C was the most popular language as per the time of the creation of the slide, but it's still the second one. If we can click the site, you can see here next to the Python, C is the uh, next popular language. So what's the reason? And C++, that's surprising. So the Java has been pushed to from third to fourth, which is surprising. I remember Java also was one time popular. So, what's the reason for DC becoming so popular? That's because of the providing the flexibility to have the complete control over the hardware resources without any additional constraint. So it's left to the programmer itself to make essential um, uh, precautionary steps to ensure the security of the program. And because the higher level, once you make you develop the language to incorporate those additional features, the language become slow enough, it won't be fast enough, uh, because of the so much of the additional constraints that it has to perform on the background. uh, and it won't be fast enough to be deployed for the devices such as embedded devices that have very little computing power or processing power. So the C is the best one that can be deployed even for the low power architecture such as embedded devices, which will provide the fast uh, which enable us to develop fast languages. And also, as we mentioned, it's a very good portable. Uh, it has a very good portable feature, so it can be ported to different architectures. So yeah, so because of that, we have to take care of any memory corruptions. So this is one of the thing uh, that we are talking about it today for the memory features. The topic has been dealt in 1968 itself about how if the process can overwrite the memory dedicated to the different process. So what would happen? So the topic has already been researched in 1968 itself, uh, and so that's the thing that we are talking about. So what happens if some process corrupt the memory and affect the functioning of the normal functioning of the specific process? If you can go over some more of the languages that these high level languages uh, has inherent within it. So here, first one would be uh, I mean, the topic is a high level problem. It's about the C. So, what the problem that C gives for the programmer is that compared to other languages such as Python or Java, in which that language itself has the inherent feature to check for any memory corruption from the uh, um, uh, programmer, accidental override from the programmer. In C, it should be left to the developer itself. So he has to take care of, as shown in the example here, in which an array has been created and it's trying to access using an index that's out of bounds. And usually you won't get the uh, error in C. Uh, in the basic C. So it's up to the programmer to make precautionary efforts such that he retrieves the contents of the array within the bounds. Uh, and the second problem that the C uh, has is that of mixing of control information and data with the so as you can see here, the program is compiled such that the code goes in the text section and the dynamically generated memory is created stored in the heap is created in the heap section, and all the local variables with the return address for the context switching and other things would be at the runtime would be created allocated in the stack. And so the stack is used to hold the data part, but actually the stack also holds the control part of the data also. So it has the pointers, it has the return addresses, the pointers to other program to transfer the control. So the stack also stores both the data and the control data part. Even though the code would be in the text, you would store the pointer to the code uh, that would be pushed into the stack, and it will have the control data part in the stack itself. So this mixing of the control and data information provides it creates a vulnerability and provides a chance for the malicious attacker to circumvent or to direct the control to different area, for example his own shellcode, and make the malicious attack. That's what it explained here. So the stack will hold the return addresses that's shown in the red part, uh, and the local address also with a buffer to store to retrieve any input that has to be retrieved from the um, any input output device. And you can see here, so everything is jumbled together, and this mixing of the control and data provides a vulnerability and a chance for the malicious attacker to inject his code. The code, I mean the pointer to the code part of the code part uh, that contains the malicious code or intended code from the attacker, as you can see here. So it usually points to the code part, and it's possible for the malicious attacker to inject the code that darts into specific part in the stack or to the text part. And as we saw in the previous slides, in the last lecture slides about the first documented uh, worm or attack that happened in 80s in MIT lab by Teppan Morris, it's a kind of the buffer overflow attack only. So he is able to uh, use the vulnerability to overflow the stack and override the return address, and through that he made that the uh, the attack possible because of the overwriting of the overflow of the buffer and overwriting the return address uh, i- in the stack in the memory area. So this creates the vulnerability and the risk with the C. And the third problem with the high level languages as in C is that the mixing of data and metadata. What we mean by metadata is, as in this shown in the example of char, the string is identified. The end of the string is identified by using the null character. So, so what would happen if we intentionally the data is created with the null character in between, as we saw here in the example. For example, with the name of Professor Yan. So here the null is being injected between inserted between the Y and Yan. How it would be interpreted? It would be interpreted as the Y as a first string and the remaining as the different string. Uh, so the mixing of data and metadata can happen. And the C also doesn't provide. The other problem is that C doesn't provide uh, uh, the cleanup functionalities that has to be. It's left over to the developer to make the cleanup activities. So, for example, once if the here if here an array or a buffer of my variable is created, what would be the value that it will hold initially? As per the C, it won't be initialized to any default value. So it will have the garbage value. Similarly, for example, once the function has been exited, the value would be still be there. A garbage value would be still be there. You just the stack pointer would be reassigned to different one for different function call, but the value in the specific location in the memory would still be there, and it's open for any malicious attacker to go and read the content. So these are some of the problems that inherent with the memory and the and the demerits of using C that doesn't provide enough security features within the language itself to handle the safety features of for memory into the language itself. So it's upon the developer to take care of not to overwrite or the memory has not been read or write incorrectly and doesn't provide an opportunity for the malicious attacker to get into the memory. So we have to make sure that the memory has been cleared up after the process has been done. So that's the thing with the C. And as we said, C is still the popular languages, and it doesn't provide any feature. And it's upon the developer to take care that it has been properly initialized or it's cleared after the end, and it refers to the code refers to the exact intended memory location, and the memory is not accessed out of bounds. So, for example, so what's the so the most of the problem occurs because of overflowing with the buffer, since C doesn't provide any check to uh, see if the buffer has been overflow in reading or writing. It's upon the developer to use to implement for it, and this provides the opportunity. Most of the errors for the binary exploitation occurs because of overflowing of the stack, uh, the buffer. So we smash the buffer, we write beyond the buffer size. So what's the buffer size? So we can see here, we can take a simple example like here. So here the program expects the input from the user using the argument v, argument c, argument v from the program command line arguments, and then make it into a quotation output. So it's a simple program, but it has the potential flaw here. Uh, so it expects, for example, it takes the first argument from the user and just calls to format the string into between the quotation, and it uses the output of 16. And so this is such a simple one. Uh, you can see here, once the function is being called, the stack will be created similar to here. So the output would be of size 16, the return address for the quarter, calling for the next address, and then the return address for the quart. What would happen if the user creates more than 16 characters? Of course, it will be uh, go beyond the output, and it will override the return address, and the return address uh, it it will the return address would be invalid one, and so the pointer would be pointing to a different location, and the segmentation fault would occur. So if you can try. So, oh, sorry. So if you can copy the same code, I don't think you can copy without the number. But you can get the point. Like it would be outputting exact thing up to uh, 16 characters. But once we exceed the characters, uh, uh, it can overflow beyond. It can overflow. So, so here it has to print the output, whatever the character. So, whatever the user has entered as the argument, it takes the argument and calls the code with the argument, and it's just formatting the string with the quotation, and then it's outputs to the buffer to the output. And what if the 16 has been uh, if the characters is beyond the 16, so it will get returned after the output, and the return address will get overwritten, and and the return address will not be no more the valid return address back to the uh, code, print quoted. So this will be overwritten, and this would no more indicate the valid one. And you will get a segmentation fault because it would point to a different memory location, and we would be trying to read the different memory location. So that's the typical case that happens uh, using C, since it doesn't provide anything inherent check to see whether the buffer has been overflow or not. So that's what here mentioned. So what can we do? So where we can place a game? So the developer has to take care that uh, the buffer doesn't get overflow. It has been used within the bounds. As we already discussed in the previous class, we should not use gets function or string or the other kind of the string copy functions without checking with the sizes. So we have the inherent functions in the C libraries like the SN printf function, where you would mention about the size of the buffer to be copied. So we have to use the save functions, uh, and it's upon the developer only. So what the point here is that there is always a chance for developer to miss and create the vulnerability because of not safe handling the buffer in his code. And what the opportunity provides for the attacker, uh, so we can we can corrupt the data. That's a simple thing. We can change the code pointer uh, uh, to direct to so you can overwrite, for example, the segmentation fault that we saw. That's because we are writing to something a different pointer that's pointing to different one. uh, but we can redirect the pointer to a specific location where we have the malicious code, for example the shell code that we have, and redirect and make it uh, and compromise the system. Uh, so that's the opportunity that this unsafe handling of the memory provides. So that's one of the main thing. So the return pointer overwriting provides an ultimate power in which just by properly correctly writing the return address with a specific code that it can be jumped into for our intended code of the malicious code created by the attacker, we can get the complete control over the compromise system, compromise and get complete control over the victim system. So some of the techniques that in the advanced models will cover would be, for example, chain functionality uh, and return oriented programming. All would involve proper handling of the placing of the return address by, and that's because of the unsafe handling of the memory and the buffer. So this is one of the example that's shown. If the return address has been compromised, so you can, for example, here we can place the return address. We can place the code uh, that can jump into the addresses of the specific location, attacker location, and so the attacker input can write his arbitrary code and then place the specific return address that it can, the pointer address that it can point and make the jump to the specific location. For example, the win function that contains the malicious code, and uh, we can read the flag or the intended consequences can be done. So the takeaway is that um, the C provides, because of the inherent lack of safety features, it provides the opportunity uh, to the for the memory to get corrupted, and we can modify the memory to insert control part into the data uh, to our benefit, and we can redirect to specific part of the program, like the win function that we saw with the example of reading the flag, or to different shell code and modify, redirect to a different kind of area on the shell code, exactly the same one. and this is the um, this is the thing that we will also see uh, in your code. So this exactly similar to the win. There is a challenge where you would be placing the code into the written part of the buffer where it will redirect into a specific code, and I think that would be part of the challenge uh, in the level 3 if I am correct. And the other part that we so these are the inherent problems that we face with the C part of the code. So, and we have to make sure that the OS takes care of of like we discuss, if I remember correctly, during the shell code injection itself, we discussed that the enough precautions taken by the OS for preventing any code being executed from the shell code. If I can open it again. So we discussed already that uh, the the protection mechanism implemented from the OS part, uh, the read product and write product in the stack to prevent from uh, injecting any code part being executed from the uh, shell, from the buffer. So if we have to make this to work, if you have to make this to work, you have to compile with GCC um, no stack protection. So there is a GCC compiling option called no stack protection, and you have to compile it using the F no stack protection. Uh, so that we will discuss it in the coming the slide. Like how can we prevent this corruption to happen here? So for example, this is the code. I think this can be copied to show the vulnerability. Okay. So generally, the code will um, compile with the stack protection. In that, it won't allow for a code to be injected into the stack and run. So you have to use the F no stack attack pointer. Once again, GDB. So if we can compile F no. And then next also we have, so there are many um, uh, the protection mechanisms that has been discussed. One is the position independent executable thing that we will about to be discussed in the next one. So this is also one of the handling that the protection mechanism that we have to ensure to avoid this buffer overload. But for the purpose of our topic of study today about the vulnerability created by the buffer overflow, we can disable this the position independent execution and no stack protector. And if we compile it, overflow. Yes. Now, if I run, for example, it will probably so this code. Okay, I haven't mentioned about the code here. So in this slide we'll go over how we can protect. What are the protection mechanisms that currently we people found to overcome the limitation from the C languages in preventing the buffer overflow. That's what the topic for this slide is about, which we will go over it today. So the main causes for the we'll look at what are the causes mainly created for the buffer overflow. So we will look at the sample code and then see if for different kind of problems that we will look into it, the causes. So I just try to convey here about how the buffer overflow here. So here it tries to read, for example, out of 16 128 characters, and of course it creates a buffer overflow if the character is more than 16. So one of the reasons that we get, let me first make the error work and then see if I can. So if I run it, so it works. And if it exceeds beyond 16, it should create a segmentation. Okay, 128 fault. Large enough to 128, it should create a segmentation fault as shown here. And you can go over the thing of the stack from here. So the currently the RSP location is uh, E38, uh, and you can see some garbage values currently being uh, input here. So if I step inside and then try to, I think I remember watching the RSP also. Mix code and so it goes into the stack pointer looking for the input, and if I try, so it's now in the, if I say continue, and give breakpoint till the end. I think, I will rerun again with so so the main thing is that it contains the error code after the buffer, and once you override the buffer, the error code will get corrupted. Um, so you can see here the, and if I watch, for example, currently it has some garbage values. I expect 41 or 61. That's read from the arguments to be placed inside the stack. So now it reads here. So now we can see here the 16 characters from the here would be starting um, from here. The 16 characters would be uh, the 5 8, the 10 corresponding to 16. And if I next time if I write it, control, you can see the corruption previously that was there with the 16 plus starting of 48 here to be overwritten with some other thing 41050 that corresponds to the text portion that contains that would have the return address of the um, some other code, for example, from the ELF perspective. In this case, for the simple program in which it reads from the buffer and return back to here. The concept here is that I, it's easy to just make a segmentation fault to go beyond the uh, 16 bytes of memory from 48 plus 16 would be, for example, 10x would be 58, I, I assume. Um, and you can, once it goes and it corrupts the next placement of the buffer uh, in the stack would be the next belonging to the return address for the next functions. And uh, that's the simple one. And the other causes is that mixing of the signers. So for example, in the code that you see here, um, you see here, for example, they create a buffer here and get the value for sign, and they just checking if the sign is greater than 16, then exit, or else the read from the read the values corresponding to the size of 16. uh, and if you can see here, the size, there is a thing like unsigned and signed here, and the variable used in the library function are unsigned integers, but the default int keyword or signed integer. So the signed and unsigned in the two's complement, the most significant bit would be used for the signed bit, and so it won't correspond to exactly the 8 words. For example, 2645 would, some value would be the highest value for the integer value. If for the signed value, it would be by 2, in the sense like the minus 1, that the whole FFF would be minus 1, and overflowing would become 0. The next one would be the 0 for the underflow. The overflow would be FE minus 2 minus 3. That's the two complement in which it will increment from 0, and then the next increment would become -1, and then the why this would represent, for example, -2, not the unsigned value of largest integer number. And the comparison would compare similar to whether the unsigned comparison or signed comparison. So for example, here it uses JAA, and so the value would be different. So this mixing up of the signedness in the integer handling of the variable, like here the int, and for the inherent thing that used for int for the C library function would create the mix up and causes this uncontrolled transfer of the flow here. The same thing that applies for the integer overflow. So you may think that it's a unsigned integer, but inherently this is a signed integer. So after the f of this thing would be actually indicating a negative value and not the positive value, and the highest value after you increment to 1, it will become -1. So if, for example, EFFF would be the highest one, the next increment of one value would become overflow and it would become f of f after the most top positive value from the integer. So this overflow would occur. That makes the possible vulnerability, as you can see here, on the reading of buffer size. The same thing similar for the off by 1 error also happens because of the you consider the buffer to be, for example, the string to be of size 15, but actually the string value would be, for example, with the ending of null character at the end would actually be 16 characters, and we assume that the string to be of 15, and we will try to overwrite a string of, for example, 15 length, and it will overflow with the null character being overwritten to beyond the off by 1 error. So for example, you create a buffer, for example, a of 3, and you write a characters of 3. The next character would be overwritten beyond the buffer to the next level, for example, shown with the one orange color code. So it actually belongs to the code belonging to the buffer. And if this is a return variable pointer to your return address, this would get corrupted. So these are the potential causes that we has to be aware of for the buffer overflow error. And in the challenges, we look at let me go over the other one also. Yeah. So what are the steps that we can take care of to avoid this? One of the things would be the random using. One of the things is the canary that has been discussed. If you can watch over the other module in the dojo called memory error, you can find program safety, I think. You can see the canary as slides belonging to canary. It's nothing but using a random number and checking the random number before and after the function prologue and a function call and the return, the prologue and epilogue of the function call. This ensures that this has not been corrupted by the malicious intent for the attack, which we are not using in any of the challenges, and so not provided in the slides here. But the canary, you can get it from the recommendation that you would probably being popped up. For example, if you click here, you can see.
Hello, hackers. Welcome to video 2 of the Memory Errors module of College. I'm Jan, and today we're going to be talking about
canary here, and the
Okay.
related slides also was
Let's
available,
break
would
in
be available.
main.
And the
Run.
ASLR is the randomization of
Um,
uh, the code
Hello, hackers. Welcome
that we
to another
discussed
Pwn College video. Today we'll be talking about
previously with the
ASLR. It
NoPy.
is a
So,
it's a
so
mitigation
the attacker
for
can able to
memory
attack
errors,
only because
specifically
of
control flow
able to
hijack
aware of
attacks,
where the
and it
code is
stands for
placed.
address space
And
layout
if we
randomization.
randomize
All right. What is the idea
placement of
behind address
the
space layout
buffer
randomization?
and
Of
the
course, the
text
idea is to
every time,
randomize the layout of the
it's
address space.
impossible for the
Um,
attacker
the
to
intuition here is that
get to know where
oftentimes when
the buffer
exploiting a
location
memory
and the return
error,
address would be there to
you corrupt a
correctly
pointer. The
estimate
attacker corrupts a pointer
the
to make
return
it point
address.
somewhere else.
So
That pointer
that's
might be
the
a
idea
code
behind
pointer, and the attacker wants to hijack control flow. The pointer might be a
space
data
layer
pointer, and the
randomization.
attacker wants
You
to
can get
perform
you
controlled
can
data
look
writes.
into more details
But whenever the attacker overwrites a pointer, they have to have
by
an idea
going over
of
the
where
slides here.
to
We
point
didn't
it
have time, I
to.
think. It's
And
already one
they
time.
can do that because, for example, if you compile a program as not position independent, the attacker can look at the binary and see where in memory that program will reside.
Thing that I tried
But
to
if you turn on address space layout randomization and you
insert,
randomize where the stack is, where the
so
heap is,
for all the
where the
challenges
main program
here,
is, where all the libraries
you
are,
need to you you using the pawn tool would be it's recommended or I would say it's essential to use the pawn tool because it helps you to get connected to the binary as a process and then modify your payload and payload size depending upon as per the challenges you have to adjust to correctly estimate the location where you have to place the um, pointer for the winning address. So the pawn tool is essential once you move from levels 3 to 6 and none of them uses the canaries and hence it's not critical to look into the canaries but some of them would be using the position independent may not use the position independent binaries um, uh, may use the position independent binary. What we mean by position independent binary is the one that we um, told that we were talking about the space randomization that provides randomizing the code such that it's difficult for the attacker to exactly get to know where the code is located. And in your pawn tools, you need to use ASLR equal to false if you have to, if the challenge says that uh, no positional encoding has been implemented. Otherwise, it will take care of. In the pitch. Are there any specific questions regarding the binary exploitation? I don't think I can go over the challenge for today. Next Thursday, so the the program exploitation will involve using of all the memory errors that created and make it to specific exploitation. So next challenge we will go over all the challenges, most of the challenges of the memory errors and program exploitation on the Thursday. And as mentioned, The due date for this challenge is on 29th Monday. Good luck with your challenges. Thank you. If there is no questions, I'll close this session. Thank you.